here today to welcome Tim Rodgers, but before doing that, to acknowledge that UBC Point Grey campus is sitting on the unceded traditional and ancestral territory of the Musqueam people. And for those of you on Zoom who are coming in from other places, joining us from other places, to acknowledge the traditional owners and caretakers of those places. So Tim graciously stepped in after, whoops, some kind of recording nightmare there. Tim graciously stepped in when one of our speakers dropped out, and it's perfect timing because he's on the job market and needs not lots of talk tests, but he's an NSERC postdoctoral fellow with Amanda Giang, who can't be here regretfully today, and is also working with Rachel Scholes in civil. Yes. He's going to talk to us about urban fate and transport of chemicals, but a little extra information. He finished his PhD in chemical engineering at U of T, and apparently he's an avid birder, and other notes that Amanda provided for me. But yeah, just very, very looking forward to this talk. Thanks, Tim.
Okay, great. I'll try and get this on my thing quickly. Okay, mic test. Can people hear me? Okay, and Zoom can hear me? Seems like. Okay, great. So my name's Tim. Thank you all so much for coming to my talk. Today, I'm going to be talking about a practical guide to chemicals fate in urban areas. So to start us off, I really want to center cities in our minds. So cities like Vancouver are places of vibrant culture and arts and innovation and everything that makes life good. Lots of good food, lots of good fun. I live in a city. I'm sure many of you do too. It's a great place to live. But that same concentration of people and stuff can tend to make cities also places where people are exposed to a number of different hazards. So you're all probably familiar with the periodic smoke that comes into Vancouver. We get these big smoke events, but of course in certain parts of the city, local pollution sources make air quality a year-round problem, so not just the smoke. And around the world, urban air pollution of the indoor and outdoor variety kills up to 7 million people around the world. So it's one of the most devastating environmental problems facing the world today. That lovely skyline we can see of Vancouver also hides changes to water use. And those changes to water use mean that cities are prone to flooding, and floods are Canada's most expensive natural disasters. As I'm sure that many of you know, in Vancouver, a lot of our stormwater ends up going right into False Creek. So we have stormwater that goes into our combined sewer network, and then we have what are called combined sewer overflows, which means we get a mixture of stormwater and sewage being dumped directly into False Creek. And this causes, some water quality problems. So quick show of hands, how many people would eat a shellfish from False Creek? No one? Okay, yeah. Well, in addition to, like bacteria, like fecal coliforms, sewage also releases compounds that are known as PCBs, or polychlorinated biphenyls, into our water systems. And these have been found at high levels in False Creek sediment, at least over the last couple of decades. And so PCBs are chemicals that used to be used as lubricants and coolants in transformers, and then they are, washed off of those into our water systems, where they accumulate in these kinds of organisms. And so this problem is particularly important for First Nations groups around the Lower Mainland, whose traditional harvests have been contaminated. For instance, the Semiahmoo First Nation in Semiahmoo or Boundary Bay, they've been trying to for decades to clean up the water in their area to a point where they could restart their harvest. So they currently can't harvest because of contaminant issues, and they're trying to get that going again. A more recent example is that we discovered that a compound in car tires that is a transformation, it's like competent car tires that's used to prevent them from degrading with ozone. And that compound has a transformation product called 6-PPD-quinone. 6-PPD-quinone, it turns out, is acutely toxic to salmon. So for instance, coho salmon are extremely sensitive to this compound. And so this has caused mass fish die-offs in the Fraser River and elsewhere in sort of the Pacific Northwest. So it's a really big, serious environmental problem. So My research studies how these kinds of chemicals move around in the environment. We need to understand that in order to understand the different ways that people and ecosystems are being exposed. So traditionally, the source of concern has been with PBT, or persistent bioaccumulative and toxic compounds. So for these compounds, the concern is that as these compounds are highly lipophilic, so they accumulate in lipids, as you go higher in the trophic level, so higher in the food chain, you end up having really high levels up to toxic levels in higher order organisms, such as humans, or for the example of DDT, which is the compound you can kind of see there, bald eagles. So DDT, made famous by Rachel Carson's Silent Spring, was a compound that almost wiped out raptor populations. It made their eggs really thin, and then when they tried to incubate them, they got crushed. And so as we've tried to sort of address the issue of bioaccumulation over time, we've started to produce less bioaccumulative compounds, but this has highlighted another risk, which are PMTs, or persistent mobile and toxic compounds. So for these compounds, the source of concern is accumulation in water cycles. Here you can see a nice little water cycle. And so the problem is that because these compounds are much more hydrophilic, more water-loving, more soluble, they're poorly treated by our traditional drinking water, wastewater, and stormwater treatment systems, and can therefore accumulate to these toxic levels in a water cycle, such as the one that you see here. So my research focuses on understanding how these chemicals are moving around in cities, how people are exposed, and then how cities are exporting these chemicals to the rest of the world in order to try and design better regulations and engineered systems, and so protect our communities and our ecosystems. So today, I'm going to start off by talking about cities, climate, and contaminant fate, showing how the ways that we build our cities really impact how chemicals move through them. Then I'm going to talk about how we can use green infrastructure to improve urban water quality and hopefully protect us from at least some PMT or PBT compounds. And then all the way through, I'll be giving some practical tips for how we can build better cities and so reduce our chemicals exposures. The main tool of my research that I used are what are called multimedia models. So here, the main conceit is that we can represent the environment around us as a combination of air, of water, and then of organics. We use octanol kind of to represent organics, but generally organics. So into each of these different compartments, we can have different emissions or inflows, and then out of them, we can have, air advection or water advection or transformation in each of these compartments. And then when we put together that with transport between the different compartments, we can start to get a pretty good idea of where a chemical is going to end up, and therefore who or what or when things might be exposed to them. So I'm going to use these kind of models throughout the talk. And the first thing that I'm going to be talking about is how do chemicals behave in the urban environment. So here we have our multimedia urban model, or MUM, as we like to call it. So this is a 7-compartment multimedia model. You can see there we have an upper air, a lower air, vegetation, water, sediment, soil, and then an urban film compartment. If you've ever, made a stir fry on your stove, and then maybe made another stir fry and forgot to clean your backsplash, and then eventually you go and clean your backsplash and it's covered in this gross film. Not that any of you would ever do that, of course. But if you've ever done that, you'll notice that you get this organic film that grows. Well, there's combustion processes happening, in our outdoor urban environments all the time. And so that same thing is happening. We're getting this buildup of organics on, you can see it on windows, on our impervious surfaces. And this buildup of organics accumulates different chemicals. And then those chemicals are washed off during rain events through our stormwater systems and into our water resources. So it's this really fast, efficient pathway for contamination of water. So we took this model using a version that I developed during my PhD for persistent mobile and toxic chemicals, PMTs, and I parameterized it for 19 different cities in the Global Atmospheric Passive Sampler Megacities, so GAPS Megacities Network, which is run by my collaborator Environment Canada, Amandeep Saini. And so for each of those cities, I specified different built environment and climate parameters in order to represent the fate and behavior of compounds known as organophosphate esters. So these are compounds that are used as plasticizers and flame retardants. There's evidence that these compounds have some toxicity. They have, some carcinogenic effects, depending on the compounds. Some of them have developmental problems can be associated with them, or fertility issues, and long-range transport, meaning they get to places like Tibet or to places like the Canadian Arctic. For me, these chemicals are really interesting on sort of a broader sense because they span this really broad range of physicochemical properties. So they go all the way from sort of PMT compounds all the way to PBT compounds within the same sort of general class. So in order to apply the model, we estimated what emissions you would need in order to maintain a lower air concentration measured by my collaborator Amin, given all the other fate processes that are happening in the city at the same time. And so that gives us this simultaneous estimate of chemicals emissions and chemicals fate, and allows us to sort of start to tell some stories. So our first question here was, how do chemicals behave in the urban environment? And so to answer that, I'm going to go through a couple of examples, namely Cairo, Bogota, and Kolkata. So starting us off with Cairo, here you can see our lovely diagram of Cairo. And in Cairo, we have 1,400 kilograms per year of overall organophosphate ester emissions. Of these, about 63% are being advected, blown downwind out of the system, never touching the ground. An additional 31% are being transformed in the air compartment. So only about, that's 94% if you add those up. And so only about 4 to 6% of the overall contaminants are coming through sort of this pathway of going down to the soil and then washed off, or down through the urban film and washed off into our water. And we have about 4.3% that's going down the Nile River, through the Nile Delta, and into the Mediterranean. By contrast, in Bogota, we have 13,000 kilograms per year of overall emissions. And of these emissions, only 3.8% are going out through that air advection pathway. So only 3.8% are being blown downwind. Instead, what we see is that the major loss process is deposition to our vegetation compartment, followed by transformation in the vegetation compartment there at 39%. For the rest, we have a bunch that gets deposited to our soil, and then actually we see 24% of infiltration into our groundwater resources. And then we have the rest going off, being washed off the soil or through that urban film pathway, and about 23% is going down the Magdalena River into the Pacific. Finally, we have Kolkata. So in Kolkata, we can see that things are different once again. So we have only 3.3% of the emissions going into our vegetation compartment, and 42% going out through our air advection. Instead, the dominant loss process is the 44% going through water advection. And this is mostly being fed by that deposition to the urban film, followed by wash off from the urban film into the Hooghly River. And then, in addition to a little bit that's coming through direct soil deposition and wash off there. And we have 44% being washed downstream towards the Indian Ocean. So back to our question of, how do chemicals behave in the urban environment? Well, we can see that there is no such thing as a singular urban environment. Instead, we have lots of different urban environments, and chemicals are behaving very differently in these different urban environments. So then the next question becomes, what explains this diversity of chemicals behavior? And to answer this, we conducted a sensitivity analysis that showed there are sort of 3 main groups of parameters that were doing the lion's share of controlling of the chemicals fate in these urban areas. And those were the built environment, the physicochemical properties of the chemicals that are being emitted in each city, and then the climate of the cities. So to look at the built environment, we developed these 2 different indices. Our first one here, you can see it's the surfaces index, and this is just representing the area of the city's footprint over the area of depositional surfaces in the city. So basically, we have film and vegetation are the main places where chemicals are being deposited in a city. And so we have the log of the area of the city footprint over the area of the film plus the area of vegetation. For this index, a lower value indicates that there are more surfaces, and a higher value indicates that there are fewer surfaces. Next, we have the vegetation film index, and this tells us basically the nature of the surfaces onto which things are depositing. So here it is the log of the area of the film over the area of vegetation, and a larger value indicates a more built up city, so one with more urban film surfaces, and a smaller value indicates a more vegetated city, so one that has more vegetation. Next, we ran the model while keeping the mixture of chemicals and the climate variables constant in order to look at just the influence of the built environment on chemicals fate. And what we found was that across this city space, as I like to call it, we have basically either advection through the air up there at the top in blue, transformation in vegetation down at the bottom left in green, or advection through the water over the bottom right in purple as our dominant loss processes. If we put all of our different cities on, you can see that the 3 cities that we've already talked about sort of represent different archetypes of this chemical's fate. So Cairo is our archetypical sparse city. In Cairo, there aren't very many depositional surfaces, and so we have our chemical being blown downwind, and that is the major loss process in Cairo and cities like it. In Bogota, we have this densely vegetated city, so there's lots of surfaces. Those surfaces tend to be vegetation. And for these compounds, at least, our vegetation is acting as a fixing and transforming surface. So when things are deposited to our vegetation, they're staying there, and then they are being transformed in the vegetation transformed the vegetation. By contrast, in Kolkata, you can see we have our densely urbanized city. And here we have that deposition to the urban film surfaces, but the urban film surface is acting to mobilize that compound into our water compartment. And so then we have advection through water as our dominant loss process. So far, everything that I've shown has been fairly well explained by these two major built environment axes. But of course, everything isn't always that predictable. And so if the real world's more complicated. And so if we put in here, you can see I've put the actual dominant fate for each of these cities, given their unique climate and their unique mixture of chemicals that are being emitted. And you can see that some of them don't match up with the regions that they are in. And this is down to the influence of those other two groups of parameters I talked about before, which is their physicochemical properties and their climates. So to start off with the physicochemical properties, here we're going to look at one PMT compound on the left and one PBT compound on the right. And so you can see that for the PMT compound, our line of deposition, as I like to call it, which is sort of this line here where our depositional processes start to dominate over our air advection, that line of deposition has moved way, way up. And so what that means is that we have transformation in the vegetation and water advection dominating the overall fate of these compounds. For our PBT compound, by contrast, you can see that we have air advection dominating. That line of deposition has gone way, way down. And so for all the cities, actually, we would predict that they're all in the region where air advection is going to dominate. Of course, you can see that still here are cities of Kolkata and Bogota. They both still have fates that are different from the regions that they're in. And that's because of their different climates. So here we have the same chemical, that same PBT chemical. This time on the left, we have it in a low deposition environment, a low deposition climate. And on the right, we have it in a high deposition climate. So starting off on the left here, our low deposition climate is one that is hot, that is dry, that is windy, and has a really high ceiling or planetary boundary layer. And in these cities, you can think of it as actually a lot like Cairo. In cities like this, you can see that just air advection is going to dominate. These cities, just everything's being blown downwind. Your community maybe doesn't have to deal with it, but downwind communities are going to be having a real problem. And you can see that water advection has been basically wiped off the map. You can see there's a tiny, tiny little bit there at the bottom. If you look really close, there's a bit of purple there. By contrast, in our high deposition environment, this is one that is cool, that is wet, that is calm, and has a low ceiling. And in this environment, you can see that our line of deposition has gone way, way up. It's a high deposition environment. And you can see that water advection is dominating for Kolkata there. And then for Bogota, you can see that we actually have soil reaction as the dominant loss process. So here what's happening is that we have deposition to vegetation, followed by wash off of vegetation onto the soil, being the dominant loss process for compounds in Bogota. So to sum everything up, our first question here was, how do chemicals behave in the urban environment? And what we saw is that there's a large variability in chemicals fate between cities. There is no singular urban environment. There's a bunch of different urban environments. So what explains this diversity of chemicals behavior? We have first our built environment factors, such as the availability of depositional surfaces and then the nature of those surfaces. So are they acting to fix and transform like the vegetation compartment, or to mobilize like the film compartment? Next, we have our physicochemical properties. So for PMT compounds, we need fewer surfaces to be deposited, and their fate is therefore dominated by water advection and vegetation transformation. By contrast, for our PBT compounds, they require more surfaces to be deposited, and their fate is dominated by air advection. Finally, we have the climate. Here we looked at two different extremes. We had our low deposition climate and our high deposition climate. The low deposition climate is a lot like Cairo, hot, dry, windy, and high ceilinged. And the high deposition environment is cool, wet, calm, and low ceilinged. Is anyone else being bothered by the mic? Is it sounding bad to everyone or just to me? It's good? Okay. I was going to maybe turn it off, but okay. Okay, so anyway, next I'll go into our practice. So what does this all mean? What are our practical tips for building better cities? Well, first, we know that chemicals are going to be behaving differently in different environments. And so cities are going to be mobilizing our chemicals to the water compartment. As we increase that urban film area, we're going to be getting more chemicals depositing on that urban film and washing off into our water. So cities are mobilizing these chemicals to the water. But the other thing that my research suggests is that there's some built environment design that we can do that will help this. If we build more green space, we're moving that equilibrium over towards the left there and having more of those fixing and transforming surfaces, and therefore having our chemicals being less mobilized. Next, I want to look at what happens if we can take those surfaces and we redirect our stormwater. If we're building on this green space, we may as well use it to treat our stormwater as well. So the next thing I want to talk about is green infrastructure and urban water quality. And the question we're going to be looking at here is, how do PMTs and PBTs behave in green infrastructure systems? So the example that I'm going to be using here, the sort of model green infrastructure system that I'm going to be using, is called a stormwater bioretention cell. So this is a stormwater management technology. It consists of, you can see, an engineered media. Typically, it's fairly sandy to allow for fast infiltration. Water from a catchment like a parking lot or a roadway or something is directed into the top of the system. It can then pond up there, infiltrates through the system, and then is released either through the underdrain, which is connected directly to a sewer system or to a receiving body, or exfiltrates out of the system into the surrounding soil, or goes up through evapotranspiration. And then there's two main goals of these systems. So the first one is to restore the pre-development hydrology of an area. So this means that trying to make the hydrology look more like an undeveloped catchment. The second is to improve stormwater quality. And to look at what this meant for our PBT and PMT compounds, I developed what I call the subsurfaces sink model. So this is an 8-compartment activity-based multimedia model. You can see the diagram over there. So all this basically means is that we have a transient ponding zone. The ponding zone allows the water to infiltrate into our mobile water. That has some soil water transport. And then we have, you can see I've got a 3-compartment root model, which lets us sort of look at like different plant dynamics of uptake. And then we have the chutes. And then the top of the soil and the is connected to the air compartment. The chutes are connected to the air compartment, and the ponding zone, when it's there, is also connected to the air compartment. I developed this as sort of like a general model of contaminant transport and vegetative treatment systems. And then the version that you're looking at here is one that has been parameterized and applied to bioretention systems using results from a spike and recovery test. So in this test, what we did was we did a pulse injection of some tracer compounds, a couple of PBT compounds, and some PMTs, including some of those organophosphate esters that we looked at before. So we did this, basically took a water truck, dumped in a bunch of these different compounds in a big system outside of Toronto. This is during my PhD. We used the measurements and then interpreted them with my modeling and use my modeling to help interpret and extend those measurements in order to look at the fate of these compounds, both during the events, but also between the events, and trying to get questions of what kind of treatment are we getting, and what does treatment even mean in the circumstances anyway. So back to our main question here of how do PMTs and PBTs behave in stormwater bioretention cells? Well, maybe as you might expect, our stormwater bioretention cell is not working very well for our PMT compounds. They're basically just advecting through. We had about 64% of this PMT compound being advected through the underdrain. And remember that underdrain is the most sort of dangerous. It's the one that's most likely to go into our water systems. It's being directly connected to our stormwater or our receiving body, with only about 18% being captured by the system. So the overall fate of the PMT compounds was completely dominated by advection. Next, we have our PBT compounds, and you can see that our PBT compounds, they're really being captured by these systems. We have about 80% being captured by the system, and their fate was dominated by sorption and then subsequent transformation. So I'm running out of time, so I'm going to maybe speed up a little bit here. But basically, the next thing we wanted to look at was, can we define screening thresholds for stormwater sourced PMT compounds based on this? Basically, the idea is, of course, a PMT compound is going to be going through a stormwater bioretention cell. That's kind of tautological. That's basically what you'd expect. So here we have our hypothetical. So to look at this, we ran a bunch of hypothetical chemicals along a log KAW versus log DOC axis. So KAW basically represents the air-water partition coefficient. A higher value means that it's more volatile, and a lower value means it's less volatile. And then log DOC, that's a soil organic carbon water partition coefficient, and a larger value here means it's more likely to sorb to soil. So looking at this, what we found was that for compounds of log DOC less than about 2.75, these compounds are really highly mobile. Then for compounds that have log DOC between 2.75 and 3.75, these are potentially mobile compounds. They're potentially PMTs, depending on their fate outside of a bioretention cell and on properties beyond these two. Finally, for compounds with log DOC is greater than 3.75, these are non-mobile, and then their fate depends on the transformation half-life, where those with transformation half-lives less than about 750 hours are going to be captured, and those are going to be transformed, and those longer are not. So they may be PBT compounds or act like them, depending on the environment. I'm going to skip this summary, and I'm going to move right along to some 6-PBD quinone, which is sort of the new fun chemical to talk about, mostly because it's really dangerous to salmon and really bad. So 6-PBD quinone, quick refresher. This is a compound that when you that is produced by tires. So it's actually you have it being at 6-PBD is added to tires to protect them from ozonation. It transforms, and then that is then washed off during these big rain events into our water resources, and that kills our salmon and our trout. So my question was, can we use bioretention cells in order to prevent this chemical from getting into our waterways and so have happier and healthier water systems? Going back to my handy dandy figure, we kind of found that it's in the middle there. So we needed more data. And for that, we looked at a system along with some partners at the city of Vancouver and in UBC at system at Pine and 8th, if any of you have been by there. It's a beautiful little spot there. And we ran another spike and recovery test. You can see us mixing up our 6-PBD quinone mixture there, and we put it into our model, and this is the results. So what you can see is that basically from our measured effluent concentrations on the y-axis there, and then the time since the flow start on the x-axis, we're getting some concentration reduction. So we entered about 200 liters of 4.5 nanograms per liter 6-PBD quinone, and you can see that we're getting out about 0.15 nanograms per liter. It's hard to tell exactly how much concentration reduction there is, because in this case, this is being mixed with additional water that's coming from the water truck that's clean, but we're getting something. The other thing you can see is that our model did a pretty good job of reproducing those observed concentrations. It's maybe a little fat, but it's getting the peak right. And so we can use our model to extend and interpret our results. So of the 850 nanograms that we added to the system, what we found was we actually had greater than 95% mass reduction to the underdrain. So that's really good news for the salmon. What that means is that if you have a storm coming through, you're able to capture basically almost all of the mass that's going through, and you're going to have fairly good that mass removal. So you're hopefully going to be protecting your salmon. The next thing we wanted to look at was what would happen if we used sort of a worst case scenario. So if we had 1,000 nanograms per liter, which is about what you'd expect from a very major highway. If any of you are familiar with Toronto, this is the level that was observed on the that was coming off of the Don Valley Parkway in Toronto. So it's a very, very large highway with lots of cars going through it every day. So we did this, we simulated that in the model. And as you can see here, the results are maybe a little less good than we were saying before. So of the 1,000 nanograms per liter that we're going in, you can see we're getting about 250 to 300 nanograms per liter coming out. So that means we're getting a concentration reduction somewhere on the order of 70, 75%, but we're still getting our actual effluent concentration is higher than that coho salmon LC50. The LC50 is the concentration at which 50% of the exposed organisms are going to die, of 94 nanograms per liter. So what this is saying is if you had a large highway going through a bioretention system and into a small stream where there's less dilution, you might still be getting some impacts on salmon. But looking at it on a mass basis, again, with my model, we can see that we're still getting greater than 90%. So we're getting about 94% mass removal. We have about 6% coming out to the underdrain and about 74% being captured by the soil, with an additional 19% predicted to go out through exfiltration into the surrounding soil, where its fate is a little bit less certain. And that's something that I think we need to really look into. So what does this all mean? What are our practical guide to chemicals in urban areas? Well, first, we saw that chemicals behave differently in different environments. And so one consequence of this is that cities are going to be mobilizing our contaminants from our air into our water. Then we found that, and so what that means is that we should build more green space. This will help us move our equilibrium over to the left and allow us to have more of those fixing and transforming surfaces, and hopefully reduce our concentrations in the air and then also in the water. Next, we found that if we want to use our stormwater, these systems, our next tip is that you can use our green space in order to treat our stormwater. And this is pretty good for PBT compounds, but not so good for PMT compounds. And that is fine in some ways because this removal still helps. If we think about 6-PBD quinone, this is an example of a chemical that's not that mobile, but is being mobilized by that really fast pathway. If it was being released in, in an office or something, we wouldn't be worried about this in stormwater. And so having these systems, they can still help, and hopefully we can improve the design over time to make them work better. So anyway, thanks so much. to all the authors of my in prep works. And yeah, I'll take some questions now. Yep.
About the transport of whatever cities you have, like you mentioned, for a city like Europe, a lot of it is around, and so would it be possible to join the city hall with the city have a lot of that?
Yeah, that's the next plan, basically. Oh, sorry. So for the Zoom audience, I've turned off my mic. If you can't hear me at the back, let me know, but I just found it really irritating. So for the Zoom audience, the question was, could we couple this with a broader atmospheric regional or global atmospheric transport model and sort of look at these results on a broader level? And that's the next thing that we're working on now. So this paper was sort of focused, this paper that isn't quite out yet, but hopefully will be soon. We were focused on sort of the differences between cities. It's something that hadn't really been as well explored, I think. And so we sort of found these interesting results. But next, looking into it, but going forward, the next plan is to put it into a global atmospheric transport model and try and get like a better estimate too of just like those overall emissions. So I've been working on these chemicals, organophosphatase esters, for a long time, and I just have this like, I just want to know how many of them are being released to the environment. You know, it's just one of those just like, I don't think it matters all that much. Well, I don't think it's important, but anyway, I just want to know. Yep. Yeah, there's just other processes on there that that I didn't show. Yeah, so there's a bunch. So there's a lot of different. So in each of these compartments, there's some transformation. Oh, sorry. Why do the numbers not add to 100? So in each compartment, there's a there's a bunch of different. In each compartment, there's loss processes like transformation. So you can see here for Cairo, we've got 31% air transformation in the air. Just because it is too busy, I didn't put all the air transformation, but it's like 1 or 2% air transformation. Basically, if you add up like the loss processes that are overall, so transformation plus the advection out through the air, advection out to the water, and advection out to the soil, and then also there's a little bit of sediment burial is another loss process from the whole like city system, the city boundary. That'll add to 100. But I just haven't shown them all here.
Capture options like the H5 one.
Yeah.
What's the role of kind of extreme weather events at just hyper saturating those places with water and putting
Yeah, so we did this experiment. Sorry, the question was, what are the roles of extreme events, and are they basically remobilizing these compounds that are being captured by the soil and putting them out into the water afterwards? So I think there's a couple of questions that are still outstanding, especially for 6-PBD-quinone. So the first one is, so have you heard of the first flush effect? This is like in stormwater, if you have things that are accumulating on roads and accumulating in the environment, then you get sort of a first flush when you have that first bit of rain that goes in. And so depending on the contaminant, basically, some contaminants, you'll have this really strong first flush effect where you get a lot of the water is coming through, or a lot of the pollutant is coming through in that sort of very, very first part of the storm. And then for other contaminants, it'll be sort of more constant throughout the storm. For 6-PBD-quinone, there's sort of mixed evidence as to how much of a first flush effect there is versus a non-first flush. And so I think that's another thing that's important. So if depending on your type of storm, if you have like a consistent high concentration coming in versus just the concentration coming in that first little bit, you're going to get different answers. When we ran this experiment, we actually ran it with the water truck, and then a week later, we came through and we put the water truck through again. But this time without adding any more compound. And we found there was almost no mobilization. And when I model it, you really don't get a lot of mobilization. If you've heard of the Gustafsson leaching index, it's called the GUS index. It's basically, they use it for pesticides. And so it's an estimate of how much these compounds will be leached out of the soil from repeated rain events. These things like, say, 6-PBD-quinone are fairly not being moved by the Gustafsson index. I think that when you look at like the basically, because these systems, so the residence time in the system is like under an hour. We basically, started the water going through. We almost missed the peak because we started seeing our fluorescent dye coming out of the back end of the system before we were ready for it. It was like 2 minutes after we dumped the fluorescent dye in the top, it's going out to the bottom, right? So these systems are so fast that anything that would be leaching out is just not going to be captured, is basically what's going to happen. So these systems are fairly poorly designed for dissolved hydrophilic compounds. And so I think that, consistent leaching, it may happen, but you're more likely to just have very low capture at the beginning. And as I say, we did test it and we didn't see much leaching, although our concentrations were lower than we'd hoped. So it was below detection limit after a certain while as well. Yeah. Right. Sorry. The other part of the question was what happens in these extreme weather events, and sort of what amount of the pollutant is being moved through those extreme weather events versus being moved through smaller events, right? That's kind of like, when the soil gets saturated, you're going to have less capture. So basically, these systems, they have, let me go back to my diagram, sorry. So they're designed, so basically, there's some amount of the contaminant that's going to be coming out through the top. There's an overflow weir, basically. So the ponding zone is only like 14 centimeters tall. After that, it goes basically right into your storm sewer. And so for really large events, they aren't going to be capturing very much at all, basically. So I've been running it now. I'm running the model now for across different IDF curves, so intensity, duration, frequency events. And so looking at, like, the 5-year event, I think we had about like something like 20% of the water is overflowing. And then, of course, it's going to be 5-year 1-hour event. I think it was that was a 5-year 24-hour event, was I think 13% overflowing or something. Anyway, so you're going to be having these larger, more intense events are definitely going to be having some of that overflow. And that means you're bypassing the system altogether and you're not going to be getting any treatment, right? So the question then is, like, what percentage of this compound is being moved in those larger events versus being moved in those smaller events? And actually, I think there's another interesting question, especially for 6-CVD-quinone, which is sort of like the one that I think is most interesting here. So there's another question of, like, when does it matter the most? If you have your streams are, at their biggest bankful size, then there's a lot of dilution. So maybe your actual receiving amount is going to be lower, especially if you have a strong first flush effect, right? If there's a strong first flush effect, there's only a fixed amount of mass in the environment that's being dumped into the water. And then you have it going in with a lot of water. Well, dilution is a solution to pollution, maybe. Not really, I don't believe that, but anyway. So, that might be actually less important. So I think that there's like an open question here of what are the important events to be looking at, and like how much of the mass, and these are things we just don't know, especially for 6-CVD-quinone. So for the same system, we have like the runoff from the IDF from the different like frequency events. So, like, the 100-year, I'm running those all right now. But we also have they have 3 water years of 2014, 2016, and 2018. This is our partners at Vancouver. And so for those 3 water years, I'm also running that, like, that's my computer back home is running that right now. And so for those water years, you don't get a 5-year event every year, right? Sort of by definition. And so a lot of the water that's coming through most of the time is going to be coming through in these smaller events. These systems are doing a pretty good job of. So I think there's definitely a trade-off there. I don't know. I think it's it is a big question. Oh yeah, I mean, I guess eventually. So will the media be saturated with the compound is the question. Yeah, after a while, I think that, so for 6-CVD-quinone, for instance, we don't know exactly how what its half-life is in soil. I don't think it's that long, to be honest. I don't think it's going to be getting to a point where you're going to have it accumulating over time. So for the PBT compounds, I showed that it was that 750 hours. That was based on 2 events a month apart. So we were getting like significant accumulation with 2 events a month apart for this. The other thing is that for the compounds that are accumulating, they're mostly accumulating at the surface. So if you're thinking about sort of like a maintenance regime for these systems, it's probably going to be determined by things that aren't these organic compounds, to be honest. Maybe PCBs, if you have a lot of PCBs, but it's going to be mostly determined by metals and by things like mercury and zinc that are being accumulated at the surface as well. So there are a lot of things that are going to be in especially particle-bound stuff. And so that estimates for these systems are like on the 10 to 30-year scale. And I don't think these compounds would be very different from that. So you might have sort of similar problems. They're going to be saturated with this, but I don't think it's going to happen in a single event. It's sort of on that kind of a 10 to 30-year scale. And honestly, I think that, probably on a regulatory basis, it would be metals that are going to be triggering it. And so we also, it's a 1D model. So you can see the vertical profile as well. We don't get much leaching, so we don't get it going down very much. And for these for the compounds that are, sort of over here, in the higher DOC, those compounds are being captured like almost entirely at the surface too. So the first like 5-10 centimeters is where they're being, and that's like my modeling shows that, and it's also supported by evidence for these other sorptive compounds.
When for the compounds that you're displaying, are vegetation and soil like either storing or transforming the compounds that are benign, or is there potential for these compounds to reach out again in 5 years and
Yeah, so the question was, are these compounds sort of staying fixed in the soil or in the plants, or are they being perhaps remobilized either by the plants or when the plants die off, in the winter and stuff, are they being remobilized? So the first thing is that direct passive uptake by the plants seems to be really small. So on a mass basis, we looked at this for a couple of different compounds. We looked at it mostly in my 2022 paper, the one that this one's based off of. We used benzotriazole as sort of our example of a compound. So it's a compound that's used in like de-icing fluids and things. And it is actually, so it has some active uptake by plants. So it's actually taken up by plants more than my model shows, but still not very much. So even for that compound, if you look at like the amount of, basically we had this, so we did the spike experiment, then we waited a month until there was another natural rainfall event. And so we had measurements coming out from the natural rainfall event of fairly high levels of benzotriazole. And so that indicates that you're getting a lot of this compound is being sorbed to the soil, right? Rather than being taken up by vegetation. We didn't measure it directly in the vegetation. I think the vegetation is sort of more of an educated guess in my model at this point than it is an actual, like, I would say it's, it's order of magnitude kind of estimations. But even with that order of magnitude estimations, the most that I was able to get it when I was trying to like tweak the model to give it really, really high uptake was like 5% uptake of benzotriazole versus everything else. So I just don't think the plants are not directly doing very much in that way. There's another way that plants might operate, which is that in the rhizosphere, you can have, which is the area around the plant roots, you can have basically different enzymes and stuff mobilizing compounds. I'm working on a paper now with a friend who's working at, he's in China. He's looking at like maize fields and rice paddies to see what happens to organophosphate esters, the same kind of compounds in them. And so he shows that we showed in that paper that there's some of this effect happening. There's some of this like mobilization of the like strongly sorbed portion back into the weakly sorbed portion where it's bioavailable again by these by plant root exudates, right? But I just don't think it's like that much compared to what's going on in here. And you do get some transformation too. And then the other question then you asked was like, is transformation necessarily good or can it lead to bad products? And that is something which I know for air, they've shown that the transformation can lead to more persistent and potentially more mobile compounds. So it can be a problem. There's a really good paper by using the same data set by my collaborator Aman. I think it's in Nature or Science. They got a really good paper in, and it's by I think it's Hong et al. I can't remember. I can find it for you if you want it. But basically, it can lead to these more dangerous transformation products being released. I don't think that's happening in vegetation, and I also don't think that there's that many people going to be exposed in the vegetation. So the studies that we have looking at transformation products, at least for these compounds in vegetation, show them sort of like. So for the air, it's, you might getting more persistent secondary transformation product, right? But in the vegetation, we see that those secondary transformation products are mostly themselves being transformed. So it's sort of going down the road to mineralization is how I like to see it. Or how I like to think of it. So I'm sort of like bullish on transformation as like removal, but other people would disagree with me. And I think reasonable people can disagree there. Yeah.
Question from the Zoom audience. Could there be an overlap?
Absolutely. Yeah. So I think that, so the question for the Zoom people was that like, is there an overlap between the PMT and the PBT range, basically? So I think that's one of the things that my results with the that the results really suggest is that there's, the way that I've kind of said it is that there's no safe space for, here, let's look at this one PBT chemical. So this one PBT chemical, you can see that its fate is just totally different depending on if you're in a different climate. You know what I mean? So there's some of these chemicals are going to be mobilized. And so you might need to be thinking of these chemicals in your water resources that you normally wouldn't if you're thinking about it just like as a single, they use KOC or K or DOC as sort of a single parameter to screen. That's like in the EU, they're proposing regulations on mobility right now that give log DOC, I forget what the exact number is. I think it's like 3.5, but there's a bunch of different proposals that are being considered right now. Log DOC of around 3.5. But I think that, I think there's no safe space. You can't design a chemical that's in like that magic range of not persistent, not bioaccumulative. I think we should be screening everything for persistence and bioaccumulation. And then we should be thinking about how we can reduce persistence and toxicity, because those are the things that like are really going to be, if you have less persistent chemicals and it's just not as big of an issue, they're not going to be here forever. You're not going to have the case of PCBs where 50 years after they've been banned, we still can't eat things because of them. And then also less toxic, because obviously things shouldn't be toxic. So to me, that's sort of where I would go in green chemistry, is thinking about less persistence, less toxicity, as opposed to trying to optimize on the KOC. No time left? Okay, well, thank you all so much. I really appreciate you giving me a chance to give a talk, and yeah, look forward to chatting more in the halls and stuff.